Okay, so this is question number 17 in section 7.2. Okay. And the question is, this region that I have sketched here, it's bounded above by y equals 1 over the square root of x squared plus 1. That's that curve. It's bounded to the left by x equals -1, to the right by x equals 1, and the bottom by the x-axis. And it asks us to revolve it around some things. The first thing it asks us to revolve around is the x-axis. What happens if that region revolves around the x-axis? I've drawn a typical rectangle. If I revolve that typical rectangle around the x-axis, it's just going to be a cylinder. There's not going to be a hole in it at all. There'll be a cylinder. And so the area of the cylinder is pi r squared h. So pi r squared, the radius is going to be the distance from here, the center of revolution, where it's revolving out to there. That's the function value. Pi r, 1 over square root of x squared plus 1 times the height, pi r squared h, the height of that cylinder is dx. And we're going to integrate that, and we're actually told it's from -1 to 1. So that one's not horrible. The original problem, rotate around the x-axis. And you should actually be able to evaluate that integral. Oh, I didn't say r squared. Pi r squared h. You can evaluate that. It involves, when you square this, you got 1 over x squared plus 1. We know that antiderivative is inverse tangent of x. And the inverse tangent of 1 is pi over 4. Inverse tangent of -1 is negative pi over 4. We can do that one. That one's not terrible. Okay, now, what about then if we want to revolve that around the line y equals 1? That is this line up here. Y equals 1, up there. Notice, if I revolve a typical rectangle, if I revolve this rectangle that's there, and if I revolve it about that line up there, a typical rectangle about this line that I just drew in blue, it's going to make a washer. It's going to have a hole, and it's going to have an outer radius. And remember, the volume of a washer is pi times the outer radius squared. Let's see, from here, the outer radius is from this line all the way to there. It doesn't matter where I am. That outer radius, anywhere on this region, is 1. So that's the outer radius is 1. Inner radius now, let's calculate the inner radius. What does that look like? It's the distance from the line down to the curve. Right, it's this distance, essentially. How far is that? Well, I know this. This distance from the bottom up to there is the curve. 1 over square root of x squared plus 1. From here on up is an additional amount that would make it all the way up to 1. So the inner radius minus inner radius squared. Inner radius is 1 minus the function value. This distance from here to here is 1 minus the function value. Outer radius squared minus inner radius squared dx. That's the height of the washer. And then that's the integral from -1 to 1. I don't know if you can see all of that on the video. There you go. Now this integral, we haven't studied how to evaluate. We actually don't have in this class the tools for evaluating that. You could plug it into some sort of software like Wolfram Alpha, or I think integrals.com. I don't know if they ever took that site down, but it was part of Wolfram Alpha. Integrals.com might do it for you. Desmos will probably give you a numerical approximation of that. So there are lots of ways to get an answer, but we do not have in our toolbox right now a way to integrate that. And the last problem C there is, what if I want to revolve around this line down here? If I take that rectangle up there and revolve it about that line down here, it is going to make a washer. And the washer that it makes, let's see. Notice the inner radius from here to the bottom of the rectangle. It doesn't matter where I draw that rectangle. The inner radius is always going to be 1. And the outer radius is going to be the distance from here all the way to the top of the curve. That's the outer radius. And so that is really, this is the function value. That's always 1, telling me that the outer radius is 1 plus, I'm going to write the function value. And I'm going to write this integral on a different sheet of paper now that I've drawn the rectangles. It is pi outer radius squared. We said the outer radius was 1 plus the function. 1 plus 1 over the square root of 1 plus x squared, or x squared plus 1, same thing. That's the outer radius. Square it. Minus the inner radius squared. The inner radius is always, in this problem, the distance from here to the axis. That's 1 squared. The height of that little cylinder would be dx, and I would integrate that from -1 to 1. We don't have the tools to integrate this. It's possible to integrate it. There's ways to integrate it, but we just don't have the tools in our toolbox for integrating that. We didn't cover everything in that chapter simply for time reasons and the fact that we could throw this. You don't know how to spell that, if you've heard me say it, but wondered what the word I was saying was. Wolfram alpha. You could put all that into Wolfram alpha and it will give you the integral.